Hello and good afternoon, CTS265 Section 840 students for the Fall 2016 semester at Anne Arundel Community College. This is the CCNP route course, and this afternoon's video tutorial is going to be a tutorial on Cisco Learning Labs Discovery Activity number 18, where we're going to be investigating Cisco Express Forwarding, or CEF as it's commonly referred to. Now, before we dive into our conversation on CEF, one of the questions from last week that was asked was that you thought that switching was a layer 2 function, and this is definitely a point of confusion among many learners, where you constantly hear, oh, we're switching, and you're thinking layer 2. Well, when we're talking about switching in the context of layer 3, remember, a router is a layer 3 device. And the PDU at layer 3 is the packet. And that's why IP is a layer 3 protocol. So we've got IP packets at layer 3. And so we're not switching frames, which are your layer 2 PDUs, the protocol data unit. We're switching packets. And so actually, let me go ahead and jump to this here. So we've got the process switching, the fast switching, and CEF. We're going to talk about these. But remember that packet switching, and I'll just put SW, packet switching is layer 3. And this happens inside of your router, right? And then we've got frame switching. And we'll just put SW for switching. And remember that frame switching is a layer 2 function, and that's going to take place inside of your switch. And again, the addresses at layer 2 are the MAC addresses, your 48-bit values, and the addresses here, what we're interested in, are the IP addresses, right? And so that's the difference. But even a router, in order to be able to effectively route the packet, and if you think about it, it logically makes sense. Your packet shows up at the router on the interface here, and let's say that that is your outgoing interface. The router, just like a switch, right? A switch is doing it between ports on the switch, right? As this is our switch here. A switch is switching at layer 2, right, based off the MAC address, trying to figure out what the incoming and outgoing ports are going to be. Well, a router is doing the same thing, but it's doing it with IP packets. And so the router, when the packet comes in, it peels off that layer 2 header information, and it peeks in at the layer 3 header information, and it says, what is the destination? And so this is why we're discussing this now, because when we start to talk about policy-based routing, right, that's a source routing decision. This is a destination routing decision, normally with IP. So it looks at the layer 3 header and it says, oh, the outgoing interface is, let's just say this is gig 01, and this is gig 00. So it sees that I need to send the packet out that interface. Well, internally, inside the switch here, right, the router has to switch the packet. And what we mean when we say switch, and so let me define that for you. The process of switching the packet is simply mapping layer 2 information to the layer 3 address and then forwarding out the outgoing interface. And I'm going to talk a lot more about what we mean by mapping layer 2 information to layer 3 information. Because remember, this is going to go out on a wire, whether it's a serial link or an Ethernet link or whatever, it's going to go out onto a wire. And so we're going to have layer 2 header information that goes with it. And that's the switching process that takes place internally in the router. But it's not switching frames, right? The frames that a switch would switch. It's switching IP packets, and that's routing the packets. But in order to route the packets, the router has to internally take the packet off the wire and look at the destination IP address, make a forwarding decision based off of that, and then forward the traffic out the right interface. So it switches the packet. It switches the packet internally and sends it out. And so this will stay up here as I pull this, as I jockey back and forth between this screen and our other screen. So we're talking about SEF switching. Now, before there was SEF switching, there were two other major there were others. There was optimum switching, and I can't remember the name of, there was like a fifth one that was out there. But the three that we're interested in are process switching. And process switching is by far the slowest. You're going to find that it's available on every router and every iOS release. You have access to process switching, but you don't want it because when something's process switched, every single packet is going to hit the CPU. And so the control plane, which is where the CPU resides, the control plane is involved in every single forwarding decision for every single packet. And this can really hammer the CPU. So then Cisco said, well, we're going to, better idea here. How would we resolve the issue? Well, what if we route once and then forward many? And that's an expression that you used to hear a long time ago. Route once and then forward many. Which means with fast switching, the first packet, when you're doing fast switching on a Cisco router, the first packet hits the CPU, hits the control plane, but the CPU and iOS is smart enough, they cache that information in something called a fast cache or a forwarding cache. That way, when the subsequent packets come in, there's an initial peek, right? There's a quick sneak peek into the fast cache to see, do I already have the information required for this destination IP address? And that information it's looking for is, well, it's actually like three pieces of information. The IP next hop information, right? It's looking for that reachability information. Do I have the IP address of the next hop? Do I know the outgoing interface? And then do I have the layer 2 rewrite information, right? Which is the MAC layer header. Do I have that information already cached? If I do, great. It's a cache hit, and it's going to save me a lot of time. If I don't, oh well, we're going to process switch it, but only the first packet. And so we'll talk a little more about the advantages of and disadvantages of fast switching and SEF when we start disabling things here. So let's go ahead and dive in, and now let's talk about SEF, where right around March of '96, Cisco came out with SEF. I think it was in iOS release 12.0. And SEF basically pre-computes everything. So let's jump onto the HQ router here, and let's go from user exec into privilege exec. So how do you see what makes up SEF? Now remember, Cisco Express Forwarding, that is sort of, think of it as an umbrella, right? SEF switching is really powered by two different data structures. The first data structure is what we call the FIB, the Forwarding Information Base. Now the key thing to remember about the FIB is that it basically pre-computes lookups, right, for every single route that the router has. So if I were to say show IP SEF, for every single entry I have here, I have pre-computed the network and then the outgoing interface. And so what SEF did is it basically decoupled the routing process, right? The layer 3 switching process. It decoupled that from the control plane, from the CPU. So that once a route gets added, then everything is pre-computed. You have an entry in the FIB, which is a data structure. You've got an entry in the adjacency table, which is another data structure. Now, how is the FIB built? Remember, the FIB is built by the networks that you find in the routing table, in the RIB. So when I say show IP route, right, I've got these entries in here, and each entry that I have in my routing table is going to have an entry in the FIB. So you can see we've got the /30 and then the /32. Remember that the attached means that it's directly attached. The receive means that it's destined for this router. Drop means just that. It's going to be dropped. And so there are also some pre-entered entries that you see here, 224, 240, some other entries that have already been pre-canned in here, the quad zeros, quad 0, /8 and /32. Right, so those are already entered in there for you. But as you add routing information, right, or if you're running a dynamic routing protocol like an EIGRP, you're going to see those new entries populate in the fib. Because if there's an entry in the rib, it will have a corresponding entry in the fib when you're doing SEF switching, right? Okay, so that is Show IP SEF. Super straightforward, right? That is your forwarding information base. And again, SEF decouples the forwarding of the data plane traffic from the control plane. Because really the RIB, this global routing table here, the RIB, the routing information database, is really nothing more than a record, a master record of all of the routing information you have. It is not consulted in a SEF switching decision. What is consulted is the fib and what we're getting ready to look at, which is the adjacency table. But with the HQ router as it stands right now, we have no traffic has been generated. So we have no entries in the adjacency table. Well, that'll be easy to fix. Let's just go ahead and throw a ping out there. We'll say 10.10.10.2, which is going to be the branch 1 router. Now, you'll notice the first packet drops with the dot, the period, and then we've got 4 successes, and that's because HQ had to ARP, right? I gave it the layer 3 address, right? The 10.10.10.2, but we didn't have an ARP entry. If I say show IP ARP or just simply show ARP, we didn't have that layer 2 information for the 10.10.10.2 that's required for me to be able to send this packet along its way. Now, this is inextricably linked with the adjacency table, the ARP cache, right, or the ARP table, whatever you want to call it. So the ARP cache that we're looking at here is inextricably linked to that adjacency table because it is the ARP cache that is used to build the adjacency table. So, and that's why we had to generate that traffic. We get that ARP, and now we can see our ARP cache. So now if I say show adjacency, oops, sorry about that, did not mean to scroll down like that on you. Now when we look at the adjacency, we can see here is the address with which we're adjacent. Now that is simply a reference count. And I'm going to actually show you on some real Cisco routers how that will go, how you can basically manipulate that value. But it's a reference count for the number of times that this is referenced by other routing information. So we see the interface, right? We've got the outgoing interface and we have the IP address. But you're probably saying, well, wait a second, you said the adjacency table was going to hold the layer 2 information that I need to forward that packet. And it does, right? And let's expand this out. I'm going to say detail, show adjacency detail. And here it is, right? And this is very, very important information. So remember, SEF has created 2 mutually exclusive data structures. The first is the FIB, forwarding information base. And this has my layer 3 reachability information and my next hop. And we see this in the RIB. So the FIB uses the information that is populated into the RIB in order to create its data structure. And so here we've got the layer 3 reachability information and the next hop, right? Destination IP and the next hop that we're going to be going to, right? Or the interface that we're going out. Then we've got this new data structure here, which is called the adjacency table. And the adjacency table is what pre-computes and holds all of my layer 2 rewrite information. And it's all pre-computed. And you can see, I'm going to show you right here, it is pre-computed right here. So here is the ARP cache entry, right, for the address that we ran the ping command to. And then you see the MAC address here. This is the destination MAC address, and here is the outgoing interface. So, with the fib providing SEF the layer 3 reachability information and the next hop information, the adjacency table has the layer 2 rewrite information, and it knows that outgoing interface. If you look here, do you see anything that looks suspicious? And I shouldn't say suspicious, but rather that might just match up with something you see there. And then we have AABBCC, this, and it goes all the way to there, right? So here is the destination MAC, right? So right here is the layer 2 MAC header rewrite information. This is the destination, this is the source, and finally, these last 16 bits, remember this is hexadecimal, so we've got 4 hex characters here, so we have 16 bits. This is really 0x, because if we wrote it in hex naturally here, sorry, 0800, sorry about that, I botched the 0 there. So 0800, and that means, what is the protocol? We're using IP. And so right here, that is your adjacency table. It has all the information that SEF is going to require for the layer 2 rewrite. And that is absolutely critical. So again, combined with the layer 3 information from the fib, the adjacency table, and the fib, this is SEF switching, right? And I'm going to use sort of a loose analogy here. Think of it as like IPsec, where it's not, IPsec isn't just one thing. IPsec is made up of all kinds of things. ISACAMP, IKE, all kinds of different encryption algorithms. It's just kind of like an umbrella. And under that umbrella, these are the actual workhorses that are making the SEF technology do what it's doing. And so again, that show adjacency detail shows me the adjacency table, and I can see right here, I've got the outgoing interface information. We have all this information and all the layer 2 rewrite information for the MAC address header. And it's all pre-computed based off of the information from the fib, from the RIB, which populates the fib, and the ARP cache, which populates our adjacency table. So now let's go ahead, let's manipulate things here, and we're going to see that that number 7 should grow because we're going to introduce a new network. So we're going to go into global config, we're going to say router EIGRP1, and we're just going to go bananas here, network 0000. So we just literally enabled EIGRP on every interface, but I think do show IP EIGRP interfaces. Yeah, just Ethernet 00 and Ethernet 01, and I don't think there's even anything on Ethernet 01. So we've got our peer do show IP EIGRP neighbors, and that is over on router 2. So it looks like router 2 has been pre-configured for us. So now let's go ahead and see if I say do show IP route, anything new, anything learned here from a dynamic routing protocol. Absolutely. We've got this new guy right here. D for dual, the diffusing update algorithm. It's EIGRP, our administrative distance of 90. There is my computed distance, not the feasible distance, the computed distance. And you can see that is whom we learned it from. That is the successor, right? The successor, the next hop router, and the interface on which it was learned. And that is the IP, 192.168.110, or I should say, that is the successor route to that network. So in the RIB, we have this information. Well, let's take a look. What did the fib do when the RIB passed along this new information, saying, do show IP SEF, saying, hey, I've got some new information here. You need to take this, stick it into the fib since we're going to pre-compute everything, since we don't want to have to look things up and have it hit the CPU. So here is our network. Take a look. The next hop is right there. And there is the outgoing interface. So this information right here, we just saw this exact information where? You've got it in the RIB, the Global Routing Information Database. Because again, the RIB is nothing more than sort of a master record keeper, right? We are not looking, or I should say, when SEF switching, you're not querying the RIB. You're going to come to the fib because he gets his information from the RIB, and he's a data structure that is optimized for forwarding. So now let's see what do show adjacency shows and take a look, right? That number has incremented. And we still have the same network, right? Still shows that same address, but now let's look at the detail. And what do we see? We see that same information with that layer 2 rewrite information still there. Now let's jump into the conversation of, okay, well, I've heard that some traffic isn't SEF switched. And you're correct. So there are some certain, I don't want to call them exemptions, but there are some certain cases where the information won't be SEF switched. If you've put any kind of IP precedence information, like type of service information, if the time to live has expired, it's not going to SEF switch it. I'm trying to think. There are probably some other cases. That's all I can think of right now. The quality of service, the type of service, the IP precedence. If it hits, I believe if it's going to a tunnel interface, it might not SEF switch it. So let's dive in and take a look. So how do I know if SEF switching is even enabled? So let's say do show run include SEF. So you can see we've got IP SEF and then no IPv6 SEF. Now, this is very, very important. I'm actually going to pull up some real Cisco routers here to demonstrate this on. So what they're having us do in the lab, and if you're following along, we're on step 5. What they're having you do now is they want you to say show IP interface, and I'm using fast Ethernet, 01, right? So the text here is a little bigger. It gives us a little better conversation, and we can see everything here. So IP fast switching is enabled, right? IP SEF switching is enabled. So SEF switching is going to take precedence. If it can't be fast switched, it will try to, if it can't be SEF switched, it will try to fast switch it. And then the last resort is process switching. So let's manipulate the switching that's being used right now. And what they're going to have you do in the lab is basically turn it off. So how do I turn off SEF switching on that interface? Well, we go into global config, I say interface fast Ethernet 01, and we say no IP route cache, and what are my options? So I've got SEF flow, which is for net flow, policy and same interface, those are outside our scope here. So if I were to say no IP route cache SEF, this will turn SEF off on this interface. So if I rerun, and actually let's rerun that do show IP interface FA01, let's take a look at what just happened. So by saying that, what I've said is SEF switching is now disabled. So what's going to happen now is every packet that hits the router for the first time, right, for that source destination pair, it's going to go up to the control plane. It's going to hit the CPU, and then it's going to make an entry into the fast cache, right? So I'll say FC for fast cache. And that's just the first packet. After that, it's going to look into the fast cache and see, hey, did I cache an entry that I can use? If it did, great, we've got a cache hit. If it's not there, we have a cache miss, and then we just do this again, right? Wash, rinse, repeat. and then that packet gets forwarded out the egress interface. Okay? Because IP fast switching is now what we are using. So here's a question. If I turn SEF switching back on, and this is always an interesting use case, if I turn SEF switching back on, I simply say IP route cache SEF. Now, and actually let me go back to the no real quick. So no IP route cache SEF. If I say do show run interface FA01, we see no IP route cache SEF. When I turn that back on and say IP route cache SEF, and then rerun the do show run, it's not there. Remember, with Cisco, it is very popular, about 99% of the time, that the default setting will not be there. And so we said IP route cache SEF, that's the default, so it doesn't show up there. But let's check. Do show IP interface FA01, is SEF switching back on? And it is. IP SEF switching is enabled. Now here's the interesting use case. So how do I turn off fast switching? And they show you how to do it, but how do you think you turn fast switching off? No IP route cache by itself. And I hit enter. Now let's say do show IP interface FA01. So what do we see here? We see that IP fast switching is disabled, but what else got disabled? SEF. So by disabling fast switching, the router will automatically disable SEF. And again, this is on the specific interface. I'll talk about globally turning on, and actually we kind of did already with IP SEF, or you would say no IP SEF. But as you can see, when you disable fast switching, it disables SEF switching. And so what switching did that command, no IP route cache, just enable? You've got it. We are now process switching, so that every single packet, every single time, hits the CPU. Now, let's talk about how do we see that, right? So how would I end up seeing that? First, let me pull that command off, and we're going to say Control A. Whoops, we'll bring back the IP route cache. Do show run interface fast Ethernet 01. And then we want, and you can see it's interesting. So look, it left in there no IP route cache SEF when I took the no IP route cache off. So we need to say IP route cache SEF. And let me make sure, do show run interface FA01. That's off of there, right? Okay, good. So it's off of there. So we're SEF switching right now. So on this router, if I said do show IP route EIGRP, I've got EIGRP running between the two. I think the interface on router 2 might be down right now. Let me make sure, do show run, or do show IP interface brief, and this should be up here. Yeah, and we've got loopback addresses that are being exchanged. So the same thing on a real Cisco router. If I say do show IP SEF, right, there are my entries. And you can see the receive entry, right, it makes more sense now. We've got this loopback interface. The next hop is receive, which means me. I'm the next hop for this. I am the destination for 1111. So here is the FIB, the forwarding information database, because do show IP route, the RIB, there is my directly connected 1111 loopback interface. So let's say do show adjacency. We have nothing, right? Because again, I haven't generated any traffic. The interface on the other side is down. Do show adjacency detail. So full disclosure, right? We've nothing. So right now we have SEF switching is enabled. Do show IP interface FA01. SEF switching is enabled, and this is what we want. And a quick note on this, unless Cisco tells you in some sort of a corner case scenario that you need to turn SEF switching off, like you're debugging IP packet or you're troubleshooting something's going on, unless they tell you to turn SEF switching off, do not turn SEF switching off. Always leave it on. So we take a look at this here. we see that SEF switching is enabled. If I were to say do show proc CPU, at least I think that's the command, and there we go. And here's what we're looking for. So do show proc CPU, include IP, or input, is it? Input. Is it input? Or I'm sorry, it must be capital IP. There we go. All right. So when we take a look at IP, and there's the process I'm looking for right here, right? IP input. So let's take a step back to process switching, right? Again, process switching's available. It's on every iOS, on just about every single router. It is out there as an option. The problem is when you do process switching, I said that it hits the CPU. Well, there's a process in the CPU that has to look into the RIB when you're process switching. And that process is the IP input process. And so again, that process is going to get hit when you're doing process switching. And so we're going to see, and I haven't staged this, I don't know the results, but I'm assuming that we should see some impact when we do this. So we're going to go ahead, I'm going to bring up the interface here, FAO1, whoops, Fast Ethernet 01, and we're going to say no shut, and this is going to bring my EIGRP adjacency up along with the interface. And there it goes. Okay, great. And it's funny, the messages came out to where the neighbor adjacency was up before the line protocol came up. So if I say do show IP SEF, there is my fib. And take a look at what's in the fib. I'm receiving that 1.1.1.1 entry from router 1, and there is the next hop information. So here is my layer 3 IP address next hop reachability information in the fib, right? Built off of the information that's in my RIB, do show IP route. There's that 1.1.1.1. So now we say do show adjacency. Okay, well now I do have an adjacency because traffic is flowing over Fast Ethernet 01. Do show IP ARP. And you can see there's the 10.1.1.1, the router 1, and there's the MAC address. So let's see, do show adjacency detail. What does it look like? And this is sort of old hat, right? You've already seen this. So here's the MAC address, 001F, 6 Charlie Fox Delta 3 Charlie Alpha 3. 001 Fox 6 Charlie Fox Delta 3 Charlie Alpha 3. And I'll draw a little line down there. Because what we have next is the MAC address for the local Fast Ethernet 01 interface. 0014 1 Charlie 3 Baker 3 Charlie 1 9. And then what's my protocol? IP. So here is the destination MAC address information for the layer 2 rewrite, and here is the source information. Because remember, when the packets are being sent from, and I'll draw this, it's going to end up being backwards here. So here's router 2 and here's router 1. When those bits come in off the wire, right, as those electronic pulses come in off the wire, the layer 2 header information is going to be the first thing that router 1 is going to look at. And it's going to look at what? Is that my Fast Ethernet 01 MAC address? Is this frame destined to me, my MAC address? And I've already got that information here on router 2, so router 1, when it sends it over there, there is the layer 2 rewrite information. It's got the source and the destination. And all router 1 needs to do is take a look at that information and say, yep, the destination, hey, and make sure I pick router 1 here, hey, that's me. So then it peels off that header, and then it looks at the layer 3 information. And it says, oh, what do I see here in the header information? Well, I see the source IP address, which is going to be the outgoing interface of router 2, and I see the destination IP address. And it's the destination IP address that I now need to look into my fib and my adjacency table to figure out, okay, do I have the next hop layer 3 reachability information for this destination IP at layer 3? That information would be in the fib. If I do, I go to the adjacency table. So the first look is my fib to see, do I have the layer 3 information I need? The next hop and outgoing interface? Do I have, and if I do, right, it's a little Gantt chart here, if I do, then I look at the adjacency table. And I say, okay, I need to know when I fire this out on this interface here and it goes across to router 1, when this gets fired out on that interface, it's got to have that layer 2 header information. And look what we just happen to have right there. Everything required. And we never looked in the rib. So again, think of the rib as like a phone book, right? Yeah, it's got everybody's information in there, but does anybody look at the phone book anymore? No. You Google it, right? Or you look in your contacts list. So that is what the fib and the adjacency table are. It's way faster to simply look at the fib and get the rewrite information. It's all pre-cached. It's there in those data structures ready to go. And that is exactly what SEF switching is doing. And we see it happening here. So let's do this. Let me go ahead and I'm going to turn SEF switching off. And we're going to do it globally. So if I say no IPsef, I have just disabled SEF switching. So now when I say do show IPsef, we get IPv4 CEF not running. Okay, well, let's come over to router 1 here, and we're going to say no IPsef on this side, right? So we would be doing what kind of switching? Let's see, do show IP interface FA01. What do you think it's going to say? So when we disabled CEF, it disabled fast switching. We take a look over here on do show IP interface fast Ethernet 01. And what do we get? Fast switching is disabled. SEF switching is disabled. So what kind of switching are we doing? And so here's a command, do show SEF state. So what is the state of SEF? What am I doing? Well, we can see right here, SEF is disabled. It is not running. And we'll talk about that per destination. So remember, by default, SEF is going to use per destination load sharing. And we'll talk about the load sharing structure, the 16 slots, if you will, that can be used. And here is the universal ID, which is also commonly referred to as a hash, right? And the universal ID is used for uniqueness. And we'll talk about SEF polarization here in a second. So back to the case here. So SEF switching is not running. Fast switching is not running. And so that's going to leave us with what? You've got it. Process switching. Okay, so what we're going to do now is, let's go ahead, we're going to turn, as you can see up here again, you can see that SEF is disabled, it's not running. So distributed SEF is disabled because we don't have line cards. This is a Cisco 1841 router, so we're not going to have distributed SEF. And again, SEF switching is disabled, not running. Now, we once again see this universal per destination load sharing algorithm along with a universal ID. So by default, remember, SEF switching uses per destination load sharing, and it keeps it so that it's unique. And what we mean by that is, we talked about polarization, and polarization would be something where you would have your traffic, even though you would hope that it is being load balanced, it doesn't end up that way. And so one scenario is, let's draw this out here, and then this guy comes down to 2 routers. And then same thing here, and we've got 2 routers over here. So we've got, let's say, 32 flows coming into this router. And they get split so that 16 go this way and that 16 go this way. But when they hit this router here, if they're hashing on the exact same information, then it's going to go 16 this way. You're not going to see what you would anticipate, and green is probably not the best choice there. Let's go to blue. So you're not going to see 8 and 8. That is what you're not going to see, right? And same thing over here. We're not going to have 8 flows and 8 flows going this way and this way. Not going to happen. And so this is polarization, where all the traffic hashes continually out the same path, right? So there's no diversity, and this is what we want, right? We want it to split, and then if there were 2 more routers down here, you would want it to split evenly going this way, 4 and 4. But with polarization, we don't get that. So to avoid the polarization and to, I don't want to say ensure randomness, but to give you a better chance at randomness, we have this universal ID. And I will honestly tell you, I have no clue where that universal ID comes from. I've poked around a little bit and cannot figure out where they come up with this hexadecimal. What do we have? 1, 2, 3, 5, 6, 7, 8. So 8 times 4, so 32-bit value. I'm not sure where they come up with that. But again, it's supposed to be unique, and it's supposed to increase the chance that we will not have CEF polarization with everything hashing the same way all the time. So let's go ahead and clear that out there. All right, so that's CEF polarization. Now let's go ahead and talk about IPv6, right? Because we've just finished covering IPv6 with OSPF. We've just finished covering IPv6 with EIGRP. So let's add some IPv6 in there and talk about CEF for IPv6. If I say do show run, include CEF, you can see that by default, and actually let's bring back, there we go. By default, this is what you're going to see. You're going to see that CEF for IPv4 is actually activated, right? It'll be on by default. But what you'll also see is that CEF for IPv6 is not on by default. So again, if you wanted CEF for IPv6, that would be something that you would have to manually enable. So let's see what the requirements are, because we are going to find out that there are some requirements that we're going to have to meet. Specifically, we're going to talk about IPv6 unicast routing, but we'll see that here shortly when we go to enable it. So if I was to say IPv6 CEF and hit enter, it tells me right up front, you must enable IPv6 routing first. In fact, I'm going to say no IP CEF, because this is another requirement of CEF with IPv6. So I say no IP CEF. So again, we have no CEF enabled for IPv4 or IPv6. So when I come back and I say IPv6 unicast routing, so we'll take care of the first requirement that says we must have unicast routing enabled first. Well, we meet that requirement now. So let's pull that back and say IPv6 CEF. Now what is the requirement? Exactly, we have to have CEF for IPv4 enabled. Without CEF for IPv4 enabled, it's not going to allow me to enable CEF for IPv6. So the two requirements that we're looking at when we're talking about CEF for IPv6 is that, one, we have to have IPv6 unicast routing on, and then second, we need to make sure that we have CEF for IPv4 enabled. Again, we've got those two requirements, but once those requirements are met, then we can go ahead and we'll easily be able to get it enabled. So let's just say IP CEF. So we've got our IPv4 CEF on, and then IPv6 CEF. So now when I say do show runs, include CEF, let's fix that there. All right, we've got CEF for IPv6 and IPv4. So from the command perspective, it's very similar. It would be do show IPv6 CEF. And those are the entries that I currently have for IPv6 CEF, right? Not much going on, not much excitement. So let's kick off IPv6 router EIGRP. And 1. And let's go ahead and say EIGRP, we'll set the router ID just to 1.1.1.1. And then we're going to jump into the loopback 0 interface and say IPv6 EIGRP 1. So we'll kick off EIGRP for IPv6, and we'll just activate it on the Fast Ethernet 01 interface as well. And that'll establish our adjacency over here with, oh, I'm sorry, I just realized I was on router 2 there. So the router ID is actually going to be 2.2.2.2. Oops. So let's get back into IPv6. So IPv6 router EIGRP 1, and router ID is 2.2.2.2. So we'll come over here to router 1, and we'll go into global config, and we're going to say IPv6 router EIGRP 1, and there we go. We need IPv6 unicast routing enabled for this as well, but we can also then say IPv6 CEF and get that turned on, and then we're going to go ahead and say router, actually IPv6 router. IPv6 router EIGRP 1. EIGRP router ID is going to be 1.1.1.1. And then we'll go into interface loopback 0 and say IPv6 EIGRP 1, and then into interface, sorry about that, FA01, and say IPv6 EIGRP 1. Now, we have no IPv6 information yet on the interfaces, so let's take care of that. So interface fast Ethernet 01, IPv6 address, FE80::1 for our link local. And that's all we need for the adjacency. And so let's just get into interface loopback 0, and we're going to say IPv6 address 2001 DB8:ACAD:1:1/64 here. And that'll be good for the loopback address. Then over on 2, let's go into fast Ethernet 01, say IPv6 address FE80::2 link local. Now we should see the adjacency stand up any second here, and let's get into the loopback interface. There we go. So we have our IPv6 adjacency, and then IPv6 address 2001 DB8:ACAD:2:2/64. All right. So if I were to say do show IPv6 route EIGRP, we should see the loopback, and there it is, the 2001 network, right? So now when I say do show IPv6 CEF, do we pick that up? Absolutely we do. Take a look. There it is right there. And so again, this is the IPv6 fib. And we simply switch out the IP for IPv6 in our command syntax, and now we're looking at the IPv6 fib. Well, what about the IPv6 adjacency table? What do we have? So if I say do show adjacency, there it is. Because remember, with the adjacency command, it's just simply do show adjacency. Our protocol, right, is what's going to be different. And so before I run the command, remember, when we ran the command for adjacency detail, we see at the end of the field, we saw that the 0, well, there was no 0x there, but hexadecimal 00, there were some zeros, and then 800, right? So 0800, which is IP. Well, what are we going to see when we say detail and we take a look here? IPv6, right? Neighbor discovery is how we learned it. 86 delta delta. But again, the first 48 bits, and I believe it's right to there, is the MAC address. And then the next 48 bits is the MAC address as well. And we've got our, so we have our source MAC and we have our destination MAC, right? And this is exactly how CEF works for IPv6, the same way it works for IPv4. Again, we just get a different protocol, but the information is still there. All right, so we talked about load sharing a little bit, and the last thing, and one of the last things I want to talk about is that load share table, right? And it's in between, it's a hash that's between the fib and the adjacency table. And so let me do my best, and actually let me create some space here. Actually, we'll cruise over to here. So when we're talking about the load share table, right? And we've seen this load sharing information before, but just like you have source and destination load balancing with Ether channel, right? So if I had 5, 6, 7, 8, if I had 8 links running between switches here, And I know that's a pretty poor representation of some switches. But if I were to have 8 links, and let's say these links are all in an ether channel, and I've got a server over here that's plugged in and a server over here that's plugged in, and let's say that this is the www web server, and we've got a bunch of traffic going from this guy, right, the host, over here to the web server. Well, if these are, let's say these are 10 gig links, so I've got an aggregate of 80 gigabits per second. Well, remember that source and destination is how this is being hashed. So that specific flow, that conversation between these two endpoints, these two nodes, the host, like the user's over here, and he's trying to access the web server, it's going to hash based on source and destination by default, and it's going to pick a single link in the bundle. And once it hashes and picks that link, it's always going to pick that link for that conversation between that source and that destination, right? So, and this is always one of the things that seems to throw learners, is that, sure, we have an aggregate of 80 gigabits per second, but if these are individual 10 gigabit per second links, a single conversation can't exceed the bandwidth provided by any single link, right? So, and it's sort of the same thing when we talk about, and I'm kind of leading into the SEF load balancing here, is to when load balancing is taking place, whether you're doing the per destination load balancing, you're still going to have a hash that's going to take you through what they call a load share table. And so what that looks like is, and I'll just basically say you've got the fib here, and it's from the fib then that it looks at this load share table, and we need 16. How many do we have there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You know what I mean? All right, so we've got 16 things here, or 16 slots basically that are available for the load sharing, and then those are tied into my data structure, the adjacency table, right? Show adjacency, show IP SEF, or show IPv6 CEF, and still show adjacency. And so then it's, and actually I probably, I've never really, can I just go back one? I'll have to look at how to undo. I usually don't undo. So typically what will happen is, let's say that we've got an even share. So it's going to load balance into the forwarding information if you have more than one path, right? So let's say we had 2 equal cost paths. So one would go to this adjacency entry, to the one, let's say it's the, the gig 01, and then this one could be adjacency gig 02. But 3 would go here, 4 would go there, 5 would go here, 6 would go here. But it's this load share table that sort of drives, and the hash takes place, that universal ID that we saw takes place right here. So that's where the hashing is. It's between the fib, and the load share table, right? And there's 16 little buckets here that can be filled up by the hash based off the number of equal cost paths we have. So if we had 3 equal cost paths, that doesn't divide into 16, right? So each path would get 5. So we would have one that was not being used, right? And again, I apologize, art is definitely not my strong suit here. But hopefully you get the idea. You have the fib, and the fib says, hey, I see multiple paths, equal cost paths. So it goes through the hash based off that universal ID to try to guarantee uniqueness into the load share table. And the load share table is kind of like the gatekeeper, ensuring that things are evenly distributed across the adjacency table entries for load balancing so that you avoid SEF polarization. And so we'll wrap up with this, right? When we talk about the load sharing algorithm. And remember, I've been saying the universal ID, universal ID. Well, there are 4 basic ways that we can do load sharing. And so for this, we'll go back to the command line, and this is where we will wrap up. So we're going to head back to the command line here. There we go. So we're going to head back to the command line here. And I'm going to go into global config, and I think we're going to say IP, and I believe it is load sharing. No, it's not IP local. Give me a second here. I'm trying to remember how to tweak. Is it IPsef? Yeah, IPsef load sharing. There we go. Sorry about that. So IPsef load sharing algorithm. So you can actually pick the algorithm you're going to use. So here you go. Just like with Ether channel, remember with Ether channel you can also include the layer 4 information, right? Those TCP UDP port numbers. So if you wanted to try to use something other than the universal algorithm to make it more random, and to ensure that you don't have polarization, you could say include ports. So then there's the original, right? And this is sort of the, I guess, call it the old school, but again, I would not use the original because I believe that this was pretty susceptible to SEF polarization. Now, if your environment is super heavy on tunnels, you could use the tunnel load sharing algorithm, or universal, right? And even with universal, we could specify, check this out, we can specify our own universal ID if we think that for whatever reason the ID, the universal ID that's being provided for us isn't actually functioning. So if I was to say A, B, C, D, E, F, and what do we have? It's 1, 2, 3, 4, 5, 6, 7, 8. So A, B, C, D, E, F, and then 1, 2, 3, 4, there we go, and hit enter. So we're going to end up using that now. So if I was to say do show IP interface fast Ethernet 01, let's make sure that we've got SEF switching is enabled, and then do show IP SEF, right? So you can see everything is still functioning the way it's supposed to, and then do show what am I? It's do show IP SEF. There's something else I'm looking for here. Hold on. Not internal, not exact. Detail. Was it detail? I think it may have been detail. I'm looking for, and I'm drawing a complete blank right now, on the ID. And I don't believe that is the ID. Certainly not the ID we entered. Again, I apologize. I'm drawing a complete blank here on do show IP. It's not do show IP SEF. It's do show. It's not adjacency, and it's not adjacency detail. Do show IP SEF. Oh, SEF state. Sorry. Show SEF. Do show IP SEF state is where we're. Do show SEF state. There we go. All right. Sorry about that. And so there you go. And you can see that for IPv4, we set it to ABCDEF12, right? And you can see it's fixed because we set it. It's not being generated by the router as a quote-unquote universal ID, right? We've fixed it, and we've set the value that we wanted to use. All right, so let's recap real quickly here. We've covered a lot of ground, right? But we started out with a discussion of the 3 different types of switching that routers use. Keeping in mind that when we're talking about layer 3 switching, it's the switching of IP packets internally on the router. And so this is how routers move those packets from the ingress interface or the incoming interface to the egress interface or the outgoing interface. They peel off that layer 2 MAC address header and they look at the source and destination. They see the destination, And if we're using SEF switching, which we are, and again, that's the recommended solution, and that is what you should be running. If they're using SEF, the router looks at that destination IP address. It immediately looks in the fib to see, do I have an entry that I can use for sending this traffic along its way, for switching this traffic to the correct outgoing interface. If it sees the entry in there with the do show IP SEF, if we see the entry we're looking for in here, let's say in the case of the 1.1.1.1, there is our layer 3 information, right? That next hop reachability information is there. Then SEF says, okay, I already have this pre-canned do show adjacency detail, and I know that to get to this next hop out that interface, this is my source and destination MAC address, along with the protocol, IPv4. And so it's already staged, sort of, think of it staged in, and I don't want to use the word cache, but staged in these data structures to where all it has to do is it simply has a pointer to say, yeah, there's the information I need, and off we go. Now I have my layer 3 next hop reachability information, which I correlate to this show adjacency table detail, or show adjacency detail command. I have my layer 2 rewrite information for the MAC address header, and then we go to the outgoing interface. And never during that process do we look at the RIB, the Global Routing Information Database. We don't need to, because the RIB is simply like a phone book. It just kind of keeps track of everything, but we're not referencing that in the data plane when we're making those decisions to forward traffic. And this is why SEF is so advantageous over fast switching, which was basically sort of a slave to the rate of change in the routing table, and then process switching, which was just a train wreck because every single packet had to go to the CPU for every single conversation that was going on, right? So those were the different kinds of switching: process switching, fast switching, SEF switching. There were a couple others, but these are the three main ones, and these are the ones we're focused on, and SEF being the most important. All right, well, that's all I've got. Thanks so much for watching, and I will see you in class on Monday night. Enjoy the rest of your weekend.